This is a Feynman diagram representing a revolutionary tool that changed how we understand the universe. And here is the twist. I used this same technology to train a machine learning model 10 times faster than the usual method. And today, I'm going to show you how exactly I did that. But before we dive into the details, we need to lay the groundwork. First, I'll explain how machine learning models are normally trained and the challenges this method faces. Once we have got that done, I'll take you on an exciting journey into the world of perturbation theory, a method physicists use to estimate unknown parameters. I'll show you how this technique can be adapted to train machine learning models, making the process faster and more efficient. After covering these key concepts, we'll jump into the code demonstration and the math implementation of this new method for training linear regression. Finally, in the last chapter, I'll share a general step-by-step recipe you can use to apply this technology to train any machine learning model. So let's get started. In the early 19th century, a brilliant mathematical physicist named Augustin Louis Cauchy spent his days exploring the mysteries of mathematics and solving problems that seemed impossible to others. One question attracted him deeply. How could one find the lowest point of a mathematical landscape? Imagine a hilly terrain where you are blindfolded and your only guide is your sense of touch. How would you find the lowest valley? Cauchy believed mathematics could provide an answer. His idea was, if you are standing on a slope, you can feel the ground beneath your feet. If the ground angles downward, you can take a small step in that direction. Step by step, as you keep following the steepest path downward, you should eventually reach the lowest point. He translated this idea into a mathematical method, which he called the method of steepest descent. This method involved calculating the slope or gradient of a function at a given point and using it to guide each step toward the function's minimum value. Cauchy's method was groundbreaking for his time. It provided a systematic way to approach problems that had puzzled mathematicians for years. While his ideas were ahead of their time, they became the foundation for what we now call gradient descent. Today, this method is at the core of training machine learning models. But gradient descent has challenges. The main challenge is randomness in our starting position. To see the issue, let's go back to our hilly terrain where we wanted to find the lowest valley. Since we don't know where the lowest valley is, we have to randomly pick a location. And this is what we have to do in machine learning as well. Imagine when our random starting point is far away from the lowest valley. Then it takes too much computation to get to the destination. Another common issue is that the hilly terrain, the cost function in machine learning, might have many local minima points, where the cost is lower than the surrounding area but not the lowest possible. Depending on where we start, gradient descent might settle in one of these local minima rather than the global minimum. A similar issue is when the cost function is flat and no preferred direction exists to guide our next step. Another challenge of this method is it takes a lot of effort to compute the gradient of the cost function. Now imagine a method that gives us the answer without going into the challenges of finding the lowest valley, or technically speaking, the minimum of the cost function. Wouldn't that be nice? That is the method that modern physics uses to estimate the unknown parameters of its models. And today, I'm going to not only present that method, but show you how I trained a machine learning model 10 times faster than the conventional approach, the gradient descent. To present this alternative method, I first need to describe what is at its heart, the perturbation theory. Before I move on, let me introduce CompuFlair's consulting services offering tailored data-driven solutions like predictive analytics, risk assessment, downtime forecasting, pipeline automation, and customer behavior insight. If interested, visit our website and fill out this form to get started. Imagine trying to solve a puzzle, but the pieces don't fit perfectly together because the puzzle is just too complicated. That's what physicists faced when they tried to understand the motion of planets, the behavior of atoms, and the forces between tiny particles. Perturbation theory is like finding a clever way to solve these puzzles piece by piece by focusing on the parts we can handle first and then slowly working out the rest. Our journey began hundreds of years ago with Isaac Newton, who wanted to understand how planets moved around the sun. Newton's laws of gravity worked very well when there were just two objects, like the Earth and the Sun. But then, when a third planet like Jupiter joined the mix, the problem became incredibly hard. Instead of giving up, scientists like Joseph Louis Lagrange and Pierre-Simon Laplace came up with an idea. What if we pretend the third planet only causes a tiny disturbance or perturbation to the simple two-planet system? By treating these disturbances as small, they could approximate the motion of planets without needing to solve the impossible full puzzle. This was the first real use of perturbation theory, and it helped explain why the solar system is stable over long periods. As we move forward in time, the scene shifts to microscopic world of atoms. In the early 20th century, scientists like Niels Bohr were trying to figure out how electrons orbit the nucleus of an atom. They could solve the math for a hydrogen atom because it had only one electron. But real atoms are much messier, with many electrons interacting with each other and with outside forces like magnetic or electric fields. To deal with this system, physicists used perturbation theory again. They started with the simple solution for hydrogen and then added the effects of these extra forces as small corrections. This allowed them to predict things like how the colors of light emitted by atoms change in a magnetic field, a phenomenon called the Zeeman effect. The story doesn't stop there. In the 1930s and 40s, physicists were exploring the even stranger world of particles like electrons and photons, the particles of light. Here, perturbation theory took on a whole new life in a field called quantum field theory. This was the language of the universe at its smallest scale, where particles pop in and out of existence and interact in ways that are hard to imagine. Physicists needed to calculate what happens when particles collide, emit light, or stick together. These calculations were incredibly complex, often leading to answers that didn't make sense because they were just infinity. A breakthrough came when physicists like Richard Feynman realized they could tame these infinities by organizing their calculations into manageable steps. They started by calculating the simplest part of the interaction and then added corrections step by step, each one smaller than the last. This is where perturbation theory became essential. The method worked because for most interactions, these corrections got smaller and smaller, so the total answer eventually made sense. Richard Feynman also had a genius idea to make these calculations easier to understand. He created diagrams, now called Feynman diagrams, that are like little cartoons showing how particles interact. For example, imagine two electrons meeting. In a Feynman diagram, you draw a wiggly line between them to represent the photon being exchanged, which is the force-carrying particle of electromagnetism. These diagrams turned complicated math into a visual language that physicists could use to predict the outcome of experiments. Feynman diagrams aren't just pretty pictures. They have real power. Using them, scientists could calculate things like the probability of two particles scattering after colliding or energy levels of particles in an atom. They even helped confirm the existence of new particles and forces like the Higgs boson. In particle physics, these diagrams became the tools to unlock the mysteries of the Standard Model, which describes almost everything we know about particles and forces in the universe. But the magic of Feynman diagrams doesn't stop at tiny particles. They have also been adapted to study the behavior of many particles interacting in condensed matter systems, like electrons in a metal or atoms in a crystal. Using these diagrams, physicists can predict how materials conduct electricity or how they might behave at very low temperatures, revealing new states of matter like superconductivity. And so perturbation theory, which began as a tool to study the motion of planets, has grown into one of the most important ideas in physics. It shows us how to tackle impossible by starting simple and adding complexity in small, manageable steps. Feynman diagrams gave this method a visual life, making it easier to grasp and apply. From the orbits of planets to the dance of particles and the behavior of materials, perturbation theory plays an essential exploratory role. Before I move on, let me introduce our high-ticket bootcamp, a personalized, immersive program designed to transform you into a sought-after data scientist. With daily access to me, we'll build your online portfolio, master job-ready skills, and prepare for job interviews. We have limited the spots to ensure the quality. So to apply, go to our website and fill out this form. If a good match, we'll move on from there. Back to video. So far I talked about the history and the concepts of perturbation theory, but I haven't walked you through the systematic way how we actually use perturbation theory in modern physics and how it can be used in training machine learning models. In various areas of modern physics like statistical physics, condensed matter physics, and particle physics, we use probabilities to describe the events. And probability in all these fields has a universal form like this. On the other hand, most of machine learning models, if not all of them, can be reformulated into this probabilistic form. For example, so far in this YouTube series, we have presented the probabilistic formulation of logistic regression and deep neural networks. And I personally think the rest of the models can also be reformulated into this universal form as well, something that I'm going to try in the future. Therefore, this formula is where machine learning can connect to physics literature, so that we can immediately use the technology of perturbation theory that physicists have developed over the last few centuries to train machine learning models. In other words, to find their unknown parameters. At this point, you might ask how exactly we can use this formula together with perturbation theory to train machine learning models. I'm going to answer this question in a short and a long version. The short answer is that the z in the denominator holds all the information about the system, and it can relate to the unknown parameter of the machine learning model and data. This relationship between model and data is a simple set of equations. The solution to this set of equations would be our estimation of the model's unknown parameters. And this estimation of the parameters is technically called training the model. I know the short answer was probably confusing, so here is the longer answer. Z in this equation is called the partition function. As you know, the sum of all the possible probabilities must be equal to 1. For example, when I throw a coin, the chance of a head is 50% and the chance of a tail is also 50%. The sum of the two 50% is 100% or simply 1. The role of z in this equation is to make sure the sum over all the possibilities is 1. So z has to be equal to this equation to make sure the sum of probabilities is equal to 1. In other words, z is a normalization factor. But physicists soon realized that z is more than just a normalization factor. It actually contains the entire information of the system. Once we have the partition function, we can use it to analytically calculate some sort of averages, technically called the expectation values of the variables of the system. In machine learning, these variables of the system are just the column names of our data spreadsheet. But why are expectation values so important? because on the one hand, we can find their analytic expression using the partition function z, and on the other hand, we can use data to estimate them. Therefore, the unknown parameters of the model will be related to a bunch of numbers that come from data, and hence we have an estimation for the parameters. And that is all it takes to train a machine learning model. Now, for this whole technology to work, we need to find an analytic solution for z, which means for this sum. And most of the time, finding the analytic exact solution of the sum is impossible. Here is where we use the perturbation theory to systematically find an analytic approximation of the partition function z. And Feynman diagrams are the visual representations of the mathematical corrections that we systematically add to analytically calculate the partition function z. After reviewing the concepts, now is the time to get to the details. First, in this chapter, I will show you the code implementation of the modern physics method and how that performs compared with the conventional minimization method, that too based on old physics. And then in the next chapter, I show you the mathematical derivation of the code that I present in this chapter. Then in the last chapter, I will summarize the whole process into a general recipe that can be used for training any other machine learning model. Here is my Jupyter notebook, and in this cell I import NumPy and linear regression model libraries. In this cell, I'm going to generate a dataset that I will then use to train a linear regression using both of the methods. First, I will arbitrarily choose to have 10 columns in my spreadsheet. Next, I will randomly generate a mean vector and a covariance matrix for a multivariate Gaussian distribution. In this cell, I will use the random class of NumPy to draw 100,000 samples from the distribution. Next, I subtract the mean from the data. In the next chapter of the video, you can see the mathematics of why I am subtracting the mean. And here I define the features and the target variables of the model. That means I'm going to use x to predict y in the future. Here I use the timeIt command to assess the speed of training a linear regression using the conventional minimization method. As you can see, it took 3 seconds to train. And in this cell, I use the timeIt command to assess the speed of training a linear regression using the expectation values like in modern physics. As you can see, it took 151 milliseconds. So it is around 20 times faster than the conventional method. I have executed this code multiple times and the speeds vary since data is randomly generated each time. But the speed is always 10 times or more faster. This cell repeats the training of machine learning using the conventional method since the timeIt command takes the evaluation into a different environment than the current notebook. And here I'm printing the dot product of the unknown parameters of the model and the feature variables. This cell is the repeat of the expectation value method, again since the timeIt command makes its cell unavailable in the rest of the cells. I have printed the same dot product as in the previous method. You can see that both methods produce the same results, which means they have come to the same estimation for unknown parameters. In this cell, we predict the target variables using the two methods. And finally, we plot the predicted y of each of the two methods on the y-axis versus the actual values of y on the x-axis. Now that I demonstrated the speed advantage of the new method over the conventional training method, let's get into the mathematics. Previously in this video, I showed that the probabilistic formulation of a linear regression is a multivariate Gaussian function, which looks like this. Here the vector mu and the matrix sigma are the unknown parameters of the model. By training the machine learning model, we mean to find an estimation for these using data. In this particular case, we can calculate the exact form of partition function, and here is the result. Note that for more complicated distributions, we still use this equation as our lowest approximation of the perturbation theory, then start to add analytic corrections to it. In this particular case, the corrections are just 0. To practically use partition function, we need to shift f by this term, where j is an auxiliary variable which we set back to 0 at the end of our calculations. In this block of calculations, we want to take j inside the parentheses so that we can later absorb it into x, since x is a dummy variable when inside an integral with -infinity to +infinity as its limits. And finally, here is the partition function with the auxiliary variable added to it. From here on, I can take derivatives of the partition function. The left-hand side, where I have not calculated the partition function, tells me what expectation value I am dealing with. And the right-hand side, where the integral is worked out, gives the analytic form of that expectation value in terms of the unknown parameters. For example, here this second derivative is equal to the covariance of data, which we can use data to compute and then relate it to the unknown components of the sigma matrix. Or here I can see that the first derivative of the partition function is the mean of the x minus mu, which is 0. Therefore, mu is the mean of x, which I can simply compute using data. Now that we are done with the training, we can use conditional probability to predict the last component of x, which means the last column in my spreadsheet, using the rest of the columns of the spreadsheet. Here we just need to compute the partition function of the conditional probability and, similar to what I just discussed, calculate its derivatives to find the expected values using the new distribution. And our prediction for the target variable is the expected value of the variable, the last column of the data, using the conditional probability distribution when the feature variables are given. And finally, here are the beta parameters of the linear regression which I implemented in the code. In the code, I had taken the mu to the left-hand side. At this point, we have seen how to train a linear regression using modern physics method and gain at least 10 times higher speed in comparison to the conventional minimization method based on older physics. Now the question is how we can use this same method to train other machine learning models. And here is the general recipe. Step 1. Reformulate the machine learning model to the following probabilistic form, the God equation. So far in this YouTube series, I have shown the probabilistic version of logistic regression and deep neural networks. We need to reformulate the rest of the models. Step 2. Analytically calculate the partition function z of the model using the perturbation theory. For deep neural networks, we have shown their probability is equal to the probability of the Ising model in physics. And the partition function of the Ising model is worked out to a good level in physics, so we just need to copy. Step 3. Count the number of unknown parameters and make as many number of expectation value equations by taking various types of derivatives with respect to the auxiliary variable j. Start from first order derivatives, and then second order, and then higher order derivatives, and continue going up until the number of equations is equal to the number of unknown parameters. Step 4. Compute the expectation values using data so that the equations that we derived in the previous step are for the unknown parameters of the model. Step 5. Solve the system of equations, perhaps numerically, to find the estimation of the parameters. In other words, train model. Step 6. Use the perturbation theory to analytically calculate the partition function of the conditional probability of the target variable given the feature variables, and use that to find an analytic solution for the expected value of the target variable. This expected value is our prediction for the target variable. I hope you enjoyed this video. Take care, and I'll see you in the next video.